all that gradients guarantee you is that somewhere out there, there's a step size small enough that if you take it, your loss will go down. That's cold comfort to know that there exists a small step size if you don't know what it is. Welcome back to the Math4ML exercise series. I am your host, Charles Frye. With me today, I have Scott, growth engineer at Weights and Biases. Scott and I are going to be working through the calculus exercises notebook here. We'll be working on some stuff with the little o notation and on gradient descent and on calculating gradients. And so if you want to know a little bit more about all those topics, make sure to check out the lecture videos that accompany this series. All right, so let's dive into this little o notation section here. So one of the main themes of the calculus lecture was that it's really nice to think about derivatives in this slightly different definition or slightly different sort of rearrangement of the definition of the derivative. So the normal definition of the derivative is about this limit, and it's the limit of a particular ratio. And the way that I like to think about it instead is in terms of this definition, the first line of math that you see there, that says, if I want to know what a function's value is at a point epsilon away from the current value, the gradient is something that does a linear approximation to what that value is. So that's f of x plus gradient times epsilon. So gradient times epsilon there, we've got that inner product, that dot product that we talked about in the linear algebra section. We're taking that dot product with epsilon, and that's giving us an approximation to the true value of f of x plus epsilon. So it's a linear approximation because we're doing that dot product. And it's an approximation because there's this little term here at the end, O of epsilon at the end. And what I like about this is that it's pretty easy to just box that up and just think of little o of epsilon means there's a small approximation error. Whereas when you wrap everything in a limit, you have to be very careful when you're manipulating limits directly. It's very easy for you to accidentally do something wrong and get the wrong answer, at least in my experience. And with the little o notation, I find that I don't run into that nearly as often. So in this exercise that we're going to do here, we're going to build some intuition for what little o means with some examples using this cool Python library called SymPy that does symbolic math. So if you've ever used Wolfram Alpha or Mathematica, this is like that built into Python. Have you ever seen this SymPy library before, Scott?
I have not. I did see this at the very beginning, which caught my eye. From SymPy import x, where x is actually not, I got used to use x as a variable, but here it's like what, a function or something?
Yeah. Let's talk about what that is. So the goal here is to be able to write mathematical expressions. And one of the important distinctions between a mathematical expression and something in a computer program, everything is bound to a specific value. So if you write x equals 1, then x is just something that points to the number 1. But when you write a mathematical expression, actually if you scroll up a little bit to some of those, actually just a little bit more, there x is a variable in that x is something that you can slot different values into very easily. And so SymPy is designed to give you the ability to directly manipulate expressions made of variables, as opposed to manipulating pointers to values, which is what you're really doing when you're writing programs. So that's maybe a little deeper into the world of math and computer programming than we really need to go. The main thing that we want to do here is check whether the expression f of x is little o of an expression g of x for some particular variable x. If you scroll up to the definition of little o, that might be helpful here. To say that the expression f of x is little o of g of x, that's how I read the left-hand side. To say that is to assert or imply that there is a limit of a ratio that is equal to 0. This is where that classic calculus idea about what happens to a slope as the 2 points come closer together, that classic calculus limit idea still shows up in this Frye derivative definition, but it's showing up here inside the definition of a little o. This is the definition of little o of g of x. It may be simpler to just take g of x as the identity function. It takes in its inputs, returns its outputs. That implies that the limit as x goes to 0 of f of x divided by x is 0. So what that says is x is in the limit as you get closer to 0, bigger than f of x.
Okay.
So g of x is bigger than f of x is one way of reading little o notation. It's like a strictly greater than kind of thing. You might have seen big O notation especially people who have an engineering or physics background will have seen a version of this big O notation that's like a greater than or equal to. It says that the limit as x goes to 0 of f of x over g of x is not infinite, basically. It's either like 0 or a constant.
Okay, and here I see there's this x. Is this for a given x, or is this capturing the fact that x is like a symbol here? Or
Yeah.
if this is true, will this be true for any x?
Let's start with what the interface of this is_o function is.
Okay,
Is_o takes two expressions in terms of a variable, and then it takes a variable. So you could give me an expression that might have like multiple variables in it for g of x and f of x. So you need to tell me which variable is the one that we're taking the limit with respect to. And so f of x could be 8 times x plus 3 times y. And then I would need to know which one of these is the actual variable of interest.
okay.
So that's why there's that x at the end there. But then, yes, it allows you to write all kinds of different expressions for x there in g of x and f of x.
Confusing me because there's only one variable here, but you still need to pass it to this SymPy.limit. Whereas like if it was multiple variables, you would.
Yeah. So
you'd have to specifically say which one it is.
Yeah. So you're going to be writing g's of x and f's of x here. So functions that you're going to write little SymPy expressions and pass them into this function. And as the person writing is_o, you need to tell me which variable that's in that expression to care about. But almost always, I think in every example in this notebook, there'll just be the one variable x.
Okay. And just to make sure I'm understanding this correctly, this is just a Python way of doing this exact thing. So saying this expression over this expression as the given variable tends to 0 is equal to 0. And then you're just checking if that limit is equal to 0. Okay.
Yep.
Cool.
Yeah, exactly. There's some comments there. There's the doc strings there to help folks understand what's going on there. But yeah, it's a Python way to get limits, which is really cool. I actually have started using SymPy more and more for just like little tiny math things that I normally would have gone to like wolframalpha.com to solve. There's this sort of long form explanation here of some of the stuff that Scott and I just talked about. Is_o operates on SymPy expressions and SymPy symbols. So a SymPy symbol is like that x that you pointed out, Scott. It's like a variable in math in that you can, you think of it as something that might take on lots of different values. And when it takes on different values, importantly, a bunch of other things would also change their value. If x is doubled, then, 2 times x is also doubled. Actually, go ahead and 2 times x there, just like the way you would in Python. Yeah, 2 times x.
Ooh.
And now we get a new expression.
Okay, so this is and it even prints nicely to look kind of like LaTeX or something like that.
Yeah, there is LaTeX built in to SymPy. It's the way it renders the expressions, which is pretty cool.
That is pretty cool.
Yeah. So we've got symbols, which are our variables, and then when we apply operations to them, we get expressions. And this is really very, very similar to what happens when you're writing a Python program. You have variables, and then you apply functions and operations to them, and those things are expressions in Python as well. So we build expressions the same way we might build them in Python. Go and run this cell. You'll see we've got all these different expressions here. And if you change the index, you can look at different ones. So we're going to do lots of different math operations to them. Yep. And then maybe -1 or 3. Yeah.
Cool.
So you can build expressions with numbers that are floats or ints, use those operators, and then there's a bunch of SymPy functions that are mathematical, these like mathematical functions, but you don't do it with NumPy functions. It's not np.sign will work because NumPy doesn't know anything about these like special mathematical expressions, right? I guess maybe the division is NumPy is for computing stuff and SymPy is for like calculating stuff. The way physicists use it, that term. Physicists use calculate to refer to like, writing down a mathematical expression and then like simplifying it and getting an answer. That's what SymPy helps you do.
Okay, cool. So it's more for a mathematical purpose. That's not like you actually want to shove values through it and see that. Mm-hmm. You want to like analytically understand your equations.
Yeah, that's maybe a better term. NumPy is computational and SymPy is analytical. I used it because recently I was looking into and trying to understand the logit normal density, which shows up in modeling of pandemics, actually. I wanted to calculate what its density was, and there's like an analytical formula. And I, at this point in my life, am better at Python than I am at manipulating analytical formulas for things. So to like check my work, I just put it in SymPy and SymPy gave me an answer.
Cool. I feel like people might have seen a lot of times when I've seen like how to understand a say formula, it would be like you shove a bunch of values through that maybe, and then see what maybe a Monte Carlo simulation or something like that. You would then see what the resulting function or distribution of the outputs looks like, and that's your way of understanding it. But here, I guess you're actually getting to the nitty gritty of more how a mathematician or physicist would understand the equation. Is that fair?
Yeah. Yeah, yeah. And I actually think it's really good to be able to do both. And yeah, I like to be able to jump back and forth. Go ahead and run that little example there.
Mhm.
And let's try and work through why we think that these answers are correct here. So we're calling is little o on x, x, and x. And so what that's asking is the limit of x divided by x as x goes to 0, is that equal to 0?
Okay.
So just thinking about that, this is the sort of like math exercise-iest part of this course, this like little o section here. So x divided by x, let's assume x is not 0, right? So it's some number other than 0. What's x divided by x going to be?
It's gonna be 1.
That's going to remain true as x goes to 0. And so the limit of x divided by x as x goes to 0 is going to be 1 and not 0.
Okay, so that's why it is false.
That's why it's false. Yeah. What about x squared divided by x? So same exercise. What is x squared divided by x going to be when x is not 0?
When x is not 0, what's x squared divided by x? It's going to be x.
And x is going to 0. So then the limit as x goes to 0 of x is 0.
Okay.
So
Let's have the mathiest part of the exercise.
I've made a little spot here where people are encouraged to kind of like play around with this to change what f of x and g of x are and to run the function. There's like a little thing that checks what the limit is. And then there's something that tells you whether that counts as little o or not.
Okay. So just to repeat what happened here, I just changed this to x squared just to see that we got the same answer, and we did. My imagination here is pretty limited, but okay, I could raise it to a further power and it still is true.
Maybe add something to it.
I was about to multiply something, but I'll do that next. Okay, so add something isn't, and
Right.
then maybe I'll just multiply while I'm at it.
Yeah.
Also isn't.
Right. So 2 times x, it gives us the same answer for little o as just x, right? So run this without the times 2,
Yeah.
and you get the lim is 1 and false. What this is trying to tell us is going back to the understanding of what the gradient does for you. The gradient gives you an approximation. And what we want out of our gradient approximation is that it can be as good as we want. And the way that's expressed in mathematics is that if you're close enough to 0, if you're trying to approximate the function close enough to the point that you started, does that also mean that your error will be like going down as you get closer to that point? And so if your error, to sort of close the loop here, if your error is equal to how far away you are from the starting point plus 2, then your error is always going to be at least 2. And so your approximation error, it doesn't get arbitrarily good. Your approximation is not arbitrarily good, right? It wouldn't be as good as the gradient approximation because the gradient approximation can become as good as we want as we get closer to the point where we're calculating the gradient.
Okay. Yeah, that makes sense. It's just saying you have to take a small step. If you take that small step, is the error increasing with the size of your step, or is it decrease, or is it like still small with whatever the size of your step is? Is that a way of understanding it?
Yeah. I would say for loose purposes, thinking of it as I make my step size smaller, my approximation gets better and better is the right way to think of it. That's what this little o idea is like trying to capture. And then there's this like mathematical apparatus of limits that helps us express that idea clearly. All right. So what we're going to do here is just like play around a little bit with this little o notation. And by the way, I've oriented this class more towards like programmer-y types, because that tends to be the types of people who are interested in machine learning. But if you like these like symbol manipulation mathematics things, there's like a blog post series that I wrote about the Frye derivative, this style of computing derivatives that really shows you in detail how to do these algebraic manipulations and things like that. So if that's something that's of interest to you, there's links in this notebook and I'll add it on the YouTube video as well.
Cool. Okay.
We're just going to do some like quick exercises just to build a little intuition of what it means for something to be little o of x or not. With this one, there's a bunch of expressions, and the goal is to answer these and say, is it true or is it not true that this expression is little o of x?
Okay, so that you lied to me when you said that the previous part was the most mathsiest part. Thankfully, I've got the first two already answered from before.
Yeah.
So I can say false for this one. And then if I remember correctly, this was true when it was raised to a power. And that was the one I experimented with.
Yep.
And multiply, I think this one. Okay, so I can think through this. As you decrease the size of your step, would it be x over this?
So it's 5 times x over x.
Okay, yeah, sorry. That's what I wanted to know.
The distinction here is the first argument there is x here for all of them. For the is little o, the first argument in this one is x. So we're just asking, are these things little o of x? And so that's the ratio of this thing over x is our ratio we take the limit of.
Yeah, okay. I think I missed that because here we had a sort of variable input function here. Now that's set to be x. Okay, sweet. 5 times x over x. As x tends to 0, does the error know?
Let me put it another way to you. We already know that x is not little o of x. That's that first thing you've got there, right?
Yeah.
So we know that x is not little o of x. And the reason why, do you remember? So the limit, that tells me that the limit is not 0. Do you remember what the limit was? It's actually still on the screen, funnily enough.
Was 1.
So if I multiply it by 5, do you know what's going to happen to the limit?
The limit will be multiplied by 5?
Yeah, exactly.
So, okay, I can kind of, the constants get moved out of the limit. Can I say that?
Yep. Yeah, this is actually, the way this is expressed is actually that limits are linear operations. So we talked about linearity for vector operations and matrix operations. The limit is in some sense the same thing, but applied to like sequences. And so limits are also linear. And so multiplying this by 5 just multiplies the limit by 5. And so the limit is now 5. And that limit is not 0. And so the answer here is, yeah, false.
That's helpful. And I think that helps my understanding that I can think of this as just, multiplying the limit itself. I don't have to actually consider this as some new thing that changes the rules in any way.
Right. So that's why when people write little o, nobody ever writes like little o of 5 times x. You would never really write it that way. I did that once in a paper because I really wanted to emphasize something in particular, but it's like very rare that you would have that because this is just about whether the limit is 0 or not. And all of that information about constants gets thrown away.
Simplified. And I guess it's same for big O. That's one thing you often see in big O is that you don't have to consider if it's twice it or if it's got a small constant added, you can just get rid of that and simplify it to whatever. And then there's a set that you just have to check. Is that big O correct?
So when physicists use big O and mathematicians use big O or little o, they usually think about x getting small. So we said the limit is x goes to 0. Computer scientists think about what happens when the input gets really big. So computer scientists think about big O, what happens, how many operations does it take as my input gets bigger and bigger? So that one thing that's the same is that these like multiplicative factors can be thrown out because it's not important. If you go over a list twice, that's much less important than whether you have to go over the list and also for each thing in the list, go over the list. 2n is much, much smaller than n squared once you get to really large n. Big O notation that people are maybe familiar with from an algorithms and data structures class or from like trying to reason about when their code's going to run slow or run fast, that does that same thing of hiding a lot of those kinds of details.
Okay, cool. This is the same because this is just another constant or another multiplicative factor.
Yep.
We've already figured out that this continues to be true as you raise it. And then this, I assume, doesn't affect things like it doesn't affect things here. So I can say true again. And then
I'm actually going to stop you for a second before we get to the last one. So I actually think it's useful you're not falling into my trap, which is good. But the trap here, part of the purpose of teaching is to lay traps for students where you can detect that they might not have understood something correctly so that you can help them pull themselves out of the trap and then understand things better. But so the idea there is like, if I multiply x by 1 divided by 1,000,000, I'm making x really small. I'm making x 1,000,000 times smaller. And so this term here, what this term represents is the like magnitude of our error. And people are maybe tempted, and because we often have to think in terms of like the absolute magnitudes, a million times smaller error, like that's pretty small. But it's not the case that making the error a million times smaller changes this little o.
Okay. The error, even though it's scaled by such a small number, it still doesn't change how it scales with X.
Exactly. Yeah.
Okay. It's still going to change it like linearly with how I change X.
Yes. So it is not the case that like you could just make X small enough that 1 in a million times X is arbitrarily smaller than X. It's always going to be a million times smaller than X. But X squared, on the other hand, as I make X smaller and smaller, X squared will be a million times smaller than X if X is 1 in 1,000. If X is 1 in a million, then X squared will be 1 in a million squared, 1 in a million times a million, which is 1 in a trillion. So X squared will become a trillion times smaller than X. And like, if a trillion times smaller is still not enough smaller for me, then like I can make X even smaller. I can make X 1 in a trillion, and then X squared is 1 in a trillion. Whereas on the other hand, X divided by a million is always just a million times smaller.
Yeah. Okay. That makes sense.
So that's what this is trying to express. And then just like scaling something up so it seems like it would be really, really big. You can always, with X cubed, I can just keep making X smaller and smaller, and eventually it'll swamp out any effect of that multiplying by a million there.
Okay. I get you. So it's even though this number itself is very small, if this ends up being the smaller of the two, where like this has 6 zeros here or whatever, this could have 10 zeros, and now all of a sudden this is the dominant thing that
Like if I'm already at 1 in a trillion, then changing by a factor of a million is not that big of a deal. But changing by squaring has become even more of a big impact. So let's go ahead and actually just run the grader on these. It'll check that we've gotten all the answers correctly.
okay.
All right.
I haven't added SymPy.
Yeah. SymPy.exp, taking the exponential function, and it looks like I've given away the answer for you there. But what I wanted to do was actually just look at these. The first one there, little o of X is like a strictly less than symbol. X is not strictly less than X. X is less than or equal to X, but X is not strictly less than X. That was one of the things I wanted to get across in the first one. Yeah, multiplying by a constant doesn't change anything. Yeah, close to 0, X is smaller than X squared. And then finally, yeah, the exponential function is not little o of X to the n for any n. So yeah, the exponential function, maybe one way of thinking about it is as you get close to 0, this value gets close to 1.
I guess I can have a look at that if we have time. I can just do like numpy.x. Oh, I guess we don't have that. Can I?
Yeah, I wouldn't use numpy on this. What I would do is go up to.
Can I do this?
Well, it'll give you a number, but what's maybe more helpful would be to go up to the cell where you can check is little o of X here at the bottom of your screen there. Yeah. So change f of X and g of X up at the top there.
Oh, okay. Yeah.
Yeah. So change f of X to sympy.exp of X. Right. Yeah. So the limit is infinite here because the e to the X goes to 1 as X goes to 0. So if your error is scales like e to the X or e to the epsilon, then as epsilon gets small, e to the epsilon doesn't get small. It becomes order 1. And so your error is always going to be like size 1. And so the ratio of your error to how big your step is like blowing up.
Okay. That's what I was going. Sorry, that's what I was going to just check with this. Is just actually look at how the value changes as we approach 0. And I'm seeing it's like converging on, if I do this, it's converging on 1,
Yeah.
which it should be converging on 0 quicker than this.
Yeah. So go ahead and divide it by that number. Yeah. Just take sympy.exp and then, yeah, copy and paste that number. So divided by number.
Yeah. Okay. Just so I have this.
Yeah. That's smart. Yeah. So far from going to 0, this is zooming off to infinity.
Okay, cool. Yeah, that makes sense. So even if it's converging to 1, this number, as my input goes to 0, for my limit, it needs to be converging to 0. Here, it's actually making it get a lot worse.
Yeah.
Okay.
So then that means false here.
And I passed all the tests.
Great. So there's a pretty similar thing for little o of X squared, but it's so similar and like the ideas are so close that rather than going through this one, I'd rather just keep on trucking to the rest of the exercises. So folks can work through those exercises. If you have any questions, post them on YouTube, post them on the forum, and we can answer them. But I want to move on to thinking about the gradient because we've been talking about little o, which is a useful idea, helpful for building your intuition about what approximations are for, but it's not directly related to machine learning. And I want to tie what we're talking about always back to what's going on in machine learning.
Okay.
The importance of this little o notation there is that it gives us a formal way to talk about approximation and when an approximation is like a good approximation versus not a good approximation. So we can say the two things are approximately the same without all the formality. What we'd want to write in order to explain what the gradient is we would say that if we want to know what the value of a function is somewhere else, it is not equal to, but maybe almost equal to f of x plus the gradient times how far away we're looking. Epsilon there, importantly, like usually we're calculating the derivatives or gradients of functions that take in vectors as input. So epsilon here isn't just a number, but actually a vector of numbers. And so if I want to say I'm at a point x, and then I want to see what the value of the function is over here, this is my epsilon here. And so I take that direction, multiply that vector with the gradient, and that gives me how much the function will have changed if I move in that direction, approximately. Not exactly, but approximately.
Okay, just so I'm sure I understand this, we have some change in input, this epsilon, and we're trying to say, if when we add this small change to our input, it's approximately equal to our original function with the original input and some gradient times that small change that we added in.
Yes.
Is that okay?
And the important thing here is what we have now is we have an approximation to f that doesn't require us to actually use the function f directly. We have its gradient, which once I calculate gradient f of x, that just becomes a vector here. And so I just have a vector and I have the value of f of x. And now I can approximate the value of f anywhere else, not just at x, but anywhere else. I can calculate an approximate value for it. When I'm close to x, it'll be probably a good approximation. Further away, the approximation gets worse and worse. But the upshot is now I have something that may be like millions of times cheaper to compute than f to calculate this. So I now have this nice approximation that might be computationally easier to use.
Okay. Yeah, that makes sense.
And the approximation is linear. It's based on linear algebra operations. Specifically, that's a dot product there. We talked about the dot product in the linear algebra section. So that makes it maybe easy to use, easier to reason about and do math about than like a generic function. Linear functions are nice. They're simpler. And then how big is our error? We know that the error, because it's little o, must shrink at a rate faster than epsilon. So what that says is like, if you have some tolerance for error, there exists a small enough epsilon such that your error won't be too big, but we don't know that much else about it. Just knowing that a function has a gradient doesn't tell you how big your errors are going to be. Where this shows up in machine learning is that all that gradients guarantee you is that there exists a step size, that somewhere out there's a step size small enough that if you take it, your loss will go down. And that's cold comfort often to know that there exists a small step size if you don't know what it is.
And just to be more concrete, what I think you're referring to here is choosing a learning rate is like a notoriously difficult thing. And that's where it shows up in how you choose that step size is what this learning rate hyperparameter you have to set is.
Yeah. Sorry. Learning rate and step size are, I think, synonymous. But these days, I think learning rate has really taken over because step size was what the sort of like classical ML people like to call it more often, and like classical optimization. And then learning rate was the term in the neural network world, coming from like cognitive science, connectionism, thinking about this as learning, not just optimization. Step size, learning rate, same thing. So little o guarantees us that there exists a learning rate, doesn't tell us what it is. So then we have to figure it out ourselves. What I want to do is I want to play around with this thing, make use of it a bit, show you what some gradient approximations look like. So now we're going to switch gears a little bit. Rather than using SymPy, which allows us to like symbolically manipulate stuff, we're going to go over and use a different library called AutoGrad that will give us gradients for stuff. So AutoGrad gives you gradients for NumPy functions. It's basically the library that the automatic differentiation in Torch is based off of. It's also very similar to the same automatic differentiation stuff that you'll find in TensorFlow. That's what this AutoGrad thing here is for. Go ahead and run that cell.
Okay.
You may be familiar with torch.grad.
What happens when you call dot backward?
Yeah, you could think of it that way. When you call that backward, you evaluate and get a specific gradient vector at a specific point. And so you get that nabla f of x that is in the definition that up there. You get that value as a gradient. What autograd.grad does here is you give it a function f, and it gives you back a new function that is like that upside down triangle sign nabla f. So that nabla f function now takes in an x and gives you a vector.
I think you've lost me now with your terminology. Nabla, is that the same as delta?
It's an upside down triangle. So actually, yeah, go up a little bit to this right there. That's pronounced nabla. It is an upside down delta. I don't think it's actually a Greek letter. I think it was like invented by physicists. But anyway, yeah, you can think of it as the gradient symbol. I'll just call it the gradient symbol. So gradient symbol f, or grad f, is a function that takes in an x and gives you that vector you can use to approximate the function. So autograd.grad takes in a function and gives you back a new function, grad f. So then we can call that function and get, so grad identity at 2 is 1, because the identity function, the gradient is always 1. And then the constant function, the gradient is always 0.
I'm giving it a function. It's giving me now a new function that I can pass in values, and it'll tell me what the gradient of my original function would be. Is that true?
Yeah, what the gradient of the original function is at that specific point.
At that point, okay.
So there's a little bit of a confusion of terminology here because different people care about different pieces of this. So sometimes people use gradient to refer to like autograd.grad, like gradient, the operator that takes in a function and returns a new function. That's autograd.grad. Other people refer to that thing on the left there, grad identity, as like the gradient of the identity, the gradient of f that takes in the same inputs as f and returns vectors. And then other people, especially in machine learning, think of the specific values returned by that function as the gradients. When you talk about, I need to calculate gradients, I need to store my gradients, I need to apply my gradients to my parameters in order to do gradient descent, all those uses of the term are thinking of actually those final output values printed underneath the cell, the like actual concrete numbers there. So people kind of use the word gradient for all three of those things. And you just need to know from the context.
Okay.
Maybe just a quick check. Is it clear why the gradient of the constant function is always 0? Looking at that constant function there.
Yes, because it'll always return 1, which doesn't change as x changes. So the gradient the error doesn't get smaller as I change my input.
Yeah, that's an interesting way of thinking about it. So the little O term there is actually always 0. The first intuition that you threw out there is a good one. It's like, oh, this function doesn't change. And so the gradient should be 0 because if there's no change, there's no gradient. That's a useful intuition. And that's the intuition that comes a little bit more, I think, from thinking about physics and thinking of gradients in terms of like directions of motion. That's definitely a good intuition to have for doing machine learning and for thinking about gradient descent. With our linear approximation intuition that we're trying to build in this session, the idea is that if this function is constant, right, then what's the best linear approximation to a constant function?
Just that value itself, no?
Yeah. It's a flat line, I guess, is maybe the way I would put it. But I think what you said is also the same idea. So because this function is a flat line, the linear approximation to this function is also a flat line.
Yeah. That makes sense.
Great.
And it doesn't matter. Like one thing that's confusing or a little bit different here to what we've been looking at is this doesn't actually operate on the input at all. It's not like I have a different function that's 2 times x or just even the value. Here it's just 1 being returned every time.
Yeah. It's a function that ignores its input. It still takes in the input, but then it ignores it. Yeah.
The gradient of a function that doesn't do anything to the input. There's no slope, or there's
no slope, just a flat line.
Okay.
Now that we've talked a little bit about autograd, let's make use of it and use it to write this linear approximation function. This returns the linear approximation of the value f at x plus epsilon from the point x. So looking at this guy here, you'll see there's a type signature, which is helpful, right? Telling you it's taking in a function, a callable, and then 2 floating point numbers and giving you back a floating point number.
Okay.
The way this function works is it promises that if you give it a function, a value to start at, and then a place to approximate the function at, epsilon, then it will give you an approximate value of f of x plus epsilon.
Okay.
But you could just call f of x plus epsilon. That would give you the exactly correct value. But we don't want to return that. We want to return an approximation to that.
Okay. So I could do this, but I'm not. This is like actually what would be the correct value of what we're trying to approximate.
Yes.
This is the thing we're trying to approximate. I'm just going to like leave that there as a little reminder. This is the thing we're trying to approximate. So I know from above that we've learned a formula for this. That is, if I remember, it's, and maybe I won't even try to remember it. So it's the gradient plus my function evaluated at this position. And then my gradient is times this given epsilon value, which is the thing my step size.
Yeah, exactly.
So that is f evaluated at x.
Yep.
And then I just have to do my gradient. So I'll just leave that there as a little thing times my epsilon. And now I need to figure out like, what's this? Thankfully, you have just shown me how I can calculate that. This is, I'm shooting myself in the foot calling it grad because you've just told me all of the different things that this can be. But this is my autograd function evaluated at my given x.
Exactly.
It's autograd.grad of my function. But then I need to call this. This is a bit weird. So maybe I'll give this a name. I don't really like doing that. Chaining functions.
People are less comfortable with higher order functions in Python because it's not really a functional programming language. But yeah, in some languages, what you just did would be absolutely the right way to do it. But I think you're right that it's not very Pythonic.
Yeah, I just think it looks weird when you're going, I don't mind when it's dot something. That doesn't look too weird to me, but this, I prefer giving it a name.
Yeah. And I would call it grad f, just because what have you done? You've applied the gradient operator to f. You have the gradient function of f.
That's fine. And then grad f of my input.
Yeah.
And now I'm taking that and I'm multiplying it by epsilon.
Yep.
I think that should do it. Let's see.
Nailed it. Good solution there. A couple things that I just want to quickly note. So notice you multiplied those two things together, and that's what works when your function takes in a scalar value, returns a scalar value. Usually in machine learning, we think about things that take in vectors and return scalars. So then this would be a dot product instead.
Is that?
Unfortunately, you have to use np.dot explicitly here because they aren't actually vectors.
Okay.
Yeah, so that at operator is only defined for like NumPy arrays. It's not defined for floats.
And grad.
Epsilon. Yeah.
Okay.
So you get the same answer. This one would work out of the box if you were to switch around f for something that takes that takes in a NumPy array instead of just a floating point number. You didn't need that in order to solve the problem, but this is maybe what it would look more like in a real machine learning case.
What's nice about this, or at least from what I've taken away from the video, is that it's interesting and cool that this shares the same notation and works the same way for both scalar inputs with thinking about it like that. And for vectors, your gradient functions doesn't end up being some completely new thing.
Yeah, exactly. So that like Frye style really emphasizes the importance of that dot product there, which then the same basic idea, it becomes slightly different in the case of matrix valued inputs. It's not exactly dot. It's like another level of additional generalization, but it's there. And you can even go another level higher and talk about derivatives of things that take in functions. So derivatives of higher order functions. And then it's still an inner product, but now it's this different, like higher level thing. But if you think of it as a dot product from the beginning, then it's a little bit less surprising every time you go up a level and discover it's a dot product by a different name, wearing a trench coat or whatever. The last thing that I wanted to do is fully connect this back to machine learning, basically connect this to optimization by gradient descent. Gradient descent uses gradients in order to optimize functions. And that's why we're even talking about calculus in this series, right? There's lots of cool math. We aren't talking about integral calculus very much at all in this series, because integrals don't show up as much in machine learning, especially the types of machine learning that scale really well and that work the best these days. So we're talking about gradients in order to understand what happens when we do optimization, these gradient-based optimization techniques. Let's close this out. The gradient gives us a good linear guess for which direction to move to make the loss go down, because it gives us a good guess for how the loss is going to behave near the values of our parameters. So we can use that to give us new values of the parameters that we think will make the loss go down. It turns out the direction to move, and this is talked about a little bit in the lecture and in the slides, is it turns out the direction to move is actually just the gradient times -1, the negative gradient. That'll be the direction that should make the loss go down the fastest, according to our approximation. And so that's where we go. But little o tells us that there is some amount of change that we should be able to guarantee that the decrease in the loss that we can predict because we have the gradient will be bigger than that little o term, should be bigger than any other effect due to the fact that our function's not actually linear. But we don't know what that size is. We choose a size, and that's the learning rate. Usually the Greek letter for that is that eta, that n-looking Greek letter there next to the gradient, though sometimes people use alpha as well. This sort of puts all of our ideas together and uses it for machine learning. And we're just going to implement, last thing here, Scott, this gradient descent step that applies one step of gradient descent on f at x. You get an x, an f, and a learning rate, and I want the updated value for x.
Okay, I'm given an x. So I want to do my x minus my learning rate, which is passed in as learning rate. And then I want to dot product that with my gradient of my function applied at this input x. We'll go with np dot dot, and my function, we haven't actually calculated my gradient, but we can do grad f equals auto grad dot grad of f. And then we have this grad f. We can evaluate that at my given xt. Oh, I realize I've called this x and it should be xt. And that will give us our new value of x with this learning rate.
Yep. The one thing I would say, though, is this may work, but you could do a dot product between two scalars or between two vectors that are the same length. But the learning rate is just a number, right? So that little circle dot in the middle there is meant to be like multiplication.
Oh, okay, cool. That makes sense.
Yeah, I'm pretty sure that would still run, actually, because NumPy loves broadcasting. But like semantically, I think that's not quite right. Yeah, awesome. Okay, yeah, that's it. There's some nice little tests in there. There's some cute tests that check. Actually, just go ahead and put like xt plus learning rate in your implementation of the function there, just so we can see what some failed tests look like. So the tests here just check that you give the right answers on some specific problems, and that it can be used to optimize a function. So it actually checks that your gradient descent is right. So that's all the exercises for the calculus section. Next time we'll talk through the exercises on the probability section.
Cool. Thanks very much.
All right. See you then.